Okay, so we have 4 physical states that you should be familiar with in Science 9. You probably learned at least 3 of them in Science 8. And those are solid, liquid, gas. So you are responsible for knowing the symbol for solid, liquid, and gas. And it's really, really hard because we represent solid with the letter S. We represent liquid with the letter L and gas with the letter G. And we put them in little brackets. So if I were to have sodium chloride, which is table salt is a solid, yes? Okay, table salt is NaCl, sodium chloride, and it is a solid. As we all know, we can sprinkle it on our food. So we would put a little S down at the bottom. So the bottom left, or bottom right is where we write the state. You remember how we had a top left, a bottom left, a top right? Now the bottom right is where we write the state. Now, if we have a liquid, I often write my L like cursive L, just because otherwise sometimes it looks like a 1 or an I. You don't have to do that. If you just want to write it, like if you write it like this, that's okay. But for me, to be more clear for you, I would write, let's say we have water. Do you guys know the formula for water? H2O. And what state is water at room temperature? Liquid. So down at the bottom right, what are we going to write? An L. We don't do that for the states. They're always lowercase. Okay, good question though. Now, helium. Helium is a gas. So if we have helium, down at the bottom right, we are going to write the letter G. Okay. There is a 4th state that we are responsible for in grade 9, and that is represented by the letters AQ, which stands for aqueous. Okay, let's take a look at that word. Aqueous. And you can see the pronunciation aqueous. Okay, aqueous. And it means, are you guys familiar with aqua? What does aqua make you think of? Water. It means dissolved in water. So in an aqueous substance, you will actually have 2 different components. You'll have both the water and the thing that is dissolved in the water. Yes? So you'll have a liquid and you'll have something which is aqueous. Okay, so if you have salt water, for example, salt water, we would write that as NaCl aqueous, because it's not a liquid. A liquid would mean that we melted it. Did we heat up the sodium chloride until it melted? No, we dissolved it in water. Okay? So this is different from sodium chloride liquid. This would mean we heated it up and melted it. Well, it really doesn't melt very well. The melting point of salt, shall we look it up? Let's find out at what temperature salt will actually melt. This may take a moment. It's running a little slow today. What's that? 801 degrees Celsius, thank you. Okay, so we would have to get to 801 degrees Celsius. That is not very convenient. We're not doing that, say, in our household. Yes? No. But we can make salt aqueous by just dissolving it in water. Okay? So, no liquid salt at home, but definitely aqueous salt at home. And solid salt at home. I know, right? It's crazy. All right. Pardon me? Yes, very much so, yeah. It's crazy, right? Yeah. Now, I'd like you to take a look at the structure of a solid. Describe that structure to your friend. Like, what does it look like? What would let you know that this is a solid? Try and describe that structure to your friend. Okay, what are some words that we could use to describe a solid, the arrangement of the atoms in a solid, or particles in a solid? Yes? Very compact. Yes? It's tightly, everything is packed tightly. Now, is our liquid packed tightly? Take a look at the picture. Is the liquid packed tightly? Yep. Now, how about the gas? Is the gas packed tightly? No, the particles are far apart. Are we okay with the word particle? Do we know what that means? Yes? It could be an atom, it could be a molecule, just a little tiny piece of matter. Yeah. So we could tell a gas from the others, from a solid or a liquid, because its particles are far apart. How could you tell the difference between a solid and a liquid? Talk with your partner. How could you find the difference between a solid and a liquid? Okay, how could we tell a solid from a liquid? Isla, you had it? Yeah, in the solid, there's a lot of order. Okay, they're very, very organized. And the gases are also kind of random, right? Now, sadly, these particles, because it's a picture on a page, they are not moving. But you're absolutely right. Unless we get to absolute zero, which is negative 273 degrees Celsius, these particles will all be moving. Now, the particles in a solid, I don't know if you remember this from grade 8, what do the particles in a solid do? They just vibrate, they jiggle around, they just vibrate, okay? So these guys, they vibrate. How about in a liquid? Yeah, in the liquid, the particles actually move around. And then gases. Okay, they move about. There's lots of motion. Okay. So they move around fast. I would have written quickly, but I did not leave enough room for it, so I wrote fast instead. Now, aqueous substances would look like a liquid, but in between the water molecules, can you see how we have these negative things? Those would be the chlorides from the sodium chloride. And do you see how we have these positive things floating around in the water? Those would be the sodiums. The positives would have a big problem because they don't like each other. So if you want some examples of solids, iron is a solid, ice is a solid, table salt is a solid. I hope you're familiar with all of those ones. Now, liquids, sometimes you'll hear the word molten. What does the word molten mean? Melted. So if you melt your salt, and remember that was 801 degrees, Could someone please look up the melting point of iron for us? That sounds about right. Whoa, 1,500. Okay, we're gonna go with 1,500 just because it's a nice round number, but yes, holy mackerel. So water is a liquid at room temperature. There are other things that are liquids at room temperature, you know, like rubbing alcohol and things like that, but many other things have to actually be melted at higher temperatures. If you have a gas, helium is a gas, you can have water vapor. You know how your kettle, when it boils, the steam comes off, that's water vapor, okay? However, the moment you can actually see it, Jude, can you come sit here? I don't know, but you're always facing that way, right? Like you're never looking at me, you're always looking like that way. Can you stay there and look this way? Okay, cool. All right, so we got helium, which is a gas, we got water vapor, which is a gas, and we have oxygen, obviously, which is a gas. There's lots of other gases. Now it's weird to think that oxygen, which is O2, can also be aqueous. But if it wasn't able to dissolve in the water, how would the poor little fishies breathe? Yes? So oxygen actually dissolves in the water and then it goes through the gills of the fish and like disperses into their lungs. Yes? Yes. I did not mean to say lungs. I got distracted by that. I meant to say into their bloodstream. It goes through their gills and it diffuses into their bloodstream. Yeah, yeah. We talked about salt water that has dissolved salt in it. And have you heard of hydrochloric acid? We used it in our last lab, right? That was dissolved in water. That's why it looked like it did. Normally HCl is a gas, but we dissolved it in water. Okay. There is one more state that you are not responsible for. It's not even like an enriched thing, but everyone always asks me about plasma. They're like, what about plasma? It's a fantastic thing. It's really interesting. It's found in stars and in lightning, in fluorescent lamps, neon lights, and the aurora borealis, the northern lights. But we don't do a lot with plasmas in Science 9, so we're not going to worry about plasma. Yes? I probably did. Oh, oh, what did I just do? Okay. Anyway, we have, so plasma is basically a gas, but it's a gas that has a charge. But you're not responsible for that, okay? So you can just be like, okay, that's nice. Now here's a little picture showing the difference between liquid and aqueous. So if we take our table salt and we melt it, it's still just table salt. We still have the positive sodium ions, and we have the negative chloride ions, but we have nothing else. That's it. Yeah? But what's the difference between that and when we dissolve it? What do you notice over in the dissolved one? What else do we have? We have water. Okay, we've got all these little water molecules. And in fact, if you could really look at it, there would be thousands of times more water molecules than ions, but it's really hard to draw that. So, you know, this one is a mixture. So this is pure NaCl, okay, pure. So it's not a mixture. And then this one is a mixture where we have both the sodium chloride and the water. So that's the difference between aqueous, where it's dissolved in water, and liquid, where it is melted. So this one here would be liquid. This one over here would be aqueous. And I'm always trying to find good pictures of things. So here's another picture of melted NaCl. NaCl liquid. And here's another picture of NaCl aqueous. And you can see this one has a few more water molecules in amongst it. Mm-hmm. We're actually going to skip this little bit. If you are interested, then you can take a look at it, but we'll just skip that little connection to a later unit for now. Both melting and dissolving, where we turn it into a liquid and when we turn it into aqueous, those are physical changes. Now, you looked a little bit earlier, a couple weeks ago probably at this point, at what a physical change is. What does it mean for a change to be physical as opposed to chemical? Yes? There's no new substance. If you melt the salt, let's go back and look at our salt. You start with ions, sodium chloride ions, and you finish with sodium chloride ions. You don't have anything new, okay? There's no like new combination of things. Dissolving is also a physical change because you started with some water. They didn't show the water over here, but you would start with some water and some sodium chloride and you would put them together. You still would have the little Mickey Mouse waters and you would still have the sodium chloride. So you've not actually made anything new, okay? Yep. So when you melt table salt, you start with solid salt. Here it is. We add some heat and we finish with liquid salt. When we dissolve, when we make salt aqueous, we add water, or we add the salt to water, and we start with solid salt and we finish with aqueous salt, but it's still salt. It'll still taste salty. In fact, if you tasted the melted salt, if your tongue could survive the process, it would taste salty. On the other hand, your tongue would not survive the process because it would be 800 degrees Celsius. Holy man. And we are now at 10:20, and that is break time. And I'm not going to count on the bells Well, you know what? Let's give it another minute because I think that clock is fast. Maybe they'll manage to ring it correctly. I don't want us out in the hallways before everyone else and me getting in trouble with everyone. So we'll just leave it there for now. We'll watch these videos when we get back. Okay? Well, I don't know. They're like, don't let your students out of your class early, blah, blah, blah. Yeah. That, nope. And I do understand it because you don't want people in the hallways making noise while other classes are in session. Does that make sense? Yeah. So we'll just wait a minute for the bell to go. If it hasn't gone by the time my computer changes to 10:20, I will dismiss you to break. There we go. See you guys in 15 minutes. Okie dokie. All right, our second bell went. We are back in class, so please put your phones away. Go have your seats. Okay, so here we go. We are going to watch Bo Manton dissolving NaCl, whoever that is. And then we're going to mix dry ice with molten salt. So the first one is not quite as exciting, but we'll give it a go anyway. Alrighty, here we go.
When an ionic substance, such as sodium chloride, is placed in water, water molecules interact with the ions on the surface. If the salt is soluble, the attractive interactions with water molecules overcome the ionic attractions within the lattice. The solvated ions move off the surface and become separated in solution. Notice that water molecules cluster about the anions with the hydrogens directed toward the negatively charged ion. On the other hand, water molecules interact with the positively charged cations through the lone pairs of electrons on the oxygens.
Okay, so you are not responsible for knowing the details of that, but did you see the process that was happening? The little water molecules go in, they grab one of the ions off of the crystal and they pull it out into the water. And then they go in and get the next one. And then they pull it out into the water. So you end up with this mixture. Okay, so that's what happens when salt dissolves. We could also watch this one, which is very similar. Let's take a look. This one has no sound, so you just have to watch. So water has, and you don't need to know this for grade 9, but this is why it works. Water has a positive end and it has a negative end. The little Mickey Mouse ears are somewhat positive, and then the Mickey Mouse head is somewhat negative. There's our sodium ion, which is positive, and our chloride ion, which is negative. Here come the little, do you see how the little positive ends of the water molecules are kind of attaching to that negative chloride? Positive and negative attract, so those positive ends pull the negative one away. And then the negative ends of the water come in and grab the positive ion and they pull it away. Yeah, they're basically kidnapping the ions from the crystal. Yeah. So that's how a dissolving a salt is. The little waters come along and kidnap the ions away from the solid crystal. Yep. And this is what it ends up looking like it's just a great big old mixture. Okay? And now we are going to watch another one. And this one shows you molten salt this time. Don't try this one at home.
Three.
Okay, let's make this bigger. There we go.
2, 1. Oh dear. Hey guys, I'm Nate. Welcome back to the backyard. Today we've got a fun experiment that we're going to try thanks to the suggestion of YouTube user Robert Vipperman. Robert wanted to know what would happen if we mixed molten salt with either liquid nitrogen or dry ice. Well, today is not today for the liquid nitrogen test, but it is today to see what happens if we pour molten salt onto dry ice. Well, we've got our foundry, we've got our salt, and we've got some dry ice. Let's try mixing together. Now, as a first step, what we want to try and do is clean out our crucible. All of the crucibles we've got currently have residue from other projects in them. This one seems to have quite a bit of aluminum built up on the sides. We're going to try and chip out what we can, then fire up the foundry and see if we can melt out the rest and shake it out so we have a mostly clean crucible to melt our salt in. We do want a small reservoir in our dry ice to pour the salt into so it doesn't just scatter all over the place. So let's take our drill bit and try and carve a hole down into the ice just a little bit.
If there was that extra residue, but
See how well molten salt pours out of the crucible. Huh. Well, it's cooled down. It certainly bubbled a good amount, but it didn't react horrendously violently at all, at least not yet. I guess it's still possible to get there, but...
So what's happening is that the hot sodium chloride, what's it doing to the dry ice? If you heat up, do you guys know what dry ice is? It's solid what? Carbon dioxide. So dry ice is solid carbon dioxide. And carbon dioxide, dry ice, is a really interesting substance because it doesn't turn, when you heat it up, it doesn't turn directly into a liquid. It goes straight from a solid to a gas. That's why often you'll see, someone picks a piece of dry ice and they'll pop it in some water and you see this like steam coming up. That is the dry ice. It vaporizes and then it condenses on the air, okay? And what's happening here is that the sodium chloride is heating up the dry ice and it's changing from solid CO2 to a gas, CO2. Is that a chemical change or a physical change? Physical, because we started with carbon dioxide, we finished with carbon dioxide. No actual change of substance.
Even the salt that's just on our pavers has cooled down to being solid.
like our salt inside our dry ice has as well. Let's see if we can tip that out.
There you go, a nice solid chunk of salt right there.
And it doesn't look very nice because I think it looked like there was like aluminum or something like left in the crucible, and so this is contaminated salt. Okay, so it's not pure salt anymore. There was some gunk in the container in which they melted it.
I think the salt in our crucible is still liquid. Try pouring a little bit more in. Skimming some of this aluminum off the top. It's just melting more aluminum as it goes. I certainly wouldn't want to get that on me, but it's nowhere near the violent kind of reaction that we've seen in other people's channels where they pour salt into water. Ooh, no, that is still squishy. Definitely hasn't cooled down all the way. Very hot. Also very hot. Still both very hot. Alright, now I know this is probably filled with aluminum and some other trace metals, but I'm gonna lick it. Surprise of all surprises, it's salty.
Alright, now this is finally cold. It was a little less cold, but it's also a little bit thicker, and it was poured second, so that makes sense. Now, I'm going to try and break a piece off of this dry ice. We're going to see what happens if we drop this dry ice into some molten salt. Let's find out. 3, 2, 1. Bubbling, bubbling, bubbling. Kind of, not even a lot. Just a little bit of bubbling.
The dry ice is disappearing a little bit faster than if you just left it out. Not a lot.
I think so, yeah.
Oh, one of our pucks broke in half. That's kind of cool. It's got a very smooth outside, but you can see the crystalline structure has begun to form on the inside as it cooled off. Hit this with a hammer. Exploded.
What property is that? They hit it with a hammer and it broke. Brittle, that is brittle. Salt is a brittle substance.
Now it's rock salt.
Sorry, what was that? Oh yeah? Shall we try it? Okay. No, I mean, actually, we'd look it up if we want to.
We've got 2 more experiments that we want to try, and we've moved to the dome just in case things get out of hand, which I don't think will be a problem, but better safe than sorry. So let's melt up some more salt and then try our next experiment. Because I'm not really sure how this is going to react when it's going down into the crucible, I have a plan for how to dip it in there and keep myself a little ways away. I'll take the dry ice and secure it in a pair of tongs, and then I'm going to use this extended grabber thing to hold the tongs away from myself, and I'll dip that down into the crucible. I don't really think it's going to explode because neither the dry ice nor the salt will vaporize rapidly the same way normal ice would, but it is possible that some salt will cool down around the dry ice, form a shell, and then the expanding dry ice will cause that to break open. So I do want to stay a little bit away, and that's why I'm not just going to be dipping this directly down into the salt.
That's hot. Glowing hot. Yeah.
Ready? It's certainly bubbling well.
A little bit like lava.
It's quite a bit more of a reaction than I thought we would get, actually. It's spilling all over our container.
Yeah, don't eat it.
Starting to slow down.
There it is.
Now just floating on the top of the salt. My tongs have become salted together. There's just so much salt that built up on the tips. And it was in contact with the dry ice, so I think it just made it cool down. It's like a salt weld. That was pretty fun. We got a lot more bubbling action than I really thought. The last thing we want to try is to take our salt and then pour it onto a container full of broken up dry ice. So it's not just pouring it onto one flat piece of dry ice that has a hole bored into it. In this case, it's just going to be lots of pieces, and it's just going to flow all over all of it. All right, here we go. I'll take the crucible. I'm just going to pour it all over that dry ice. This could be exciting.
I don't know that this is going to be that exciting.
Ready? 3, 2, 1.
Wow, that was disappointing.
I think I expected a little bit more of a reaction when that poured on.
So he didn't actually miss it. What happened is it poured onto it. The carbon dioxide vaporized, provided a little layer that the rest of it just flowed off of. So it was like there was a little layer of gas, and the molten salt just poured right off of it. So were we wanting to look up the molten salt with water? Okay. Watermelons with what? With molten salt? Okay, why don't we take a look for that? Molten salt and water. Whoops. Oh, this one here, Backyard Scientist? Okay. Yeah, don't do this in your backyard.
You normally get a very safe product like salt water, but under special conditions, mixing the two together can result in a massive explosion. So today, that's exactly what we're going to try to do. So I first saw this video a couple months ago posted by the channel What We Made, and the guy just took some molten salt and poured it into the water. It started exploding and splattering all over the place, and I couldn't figure out why it was happening. Was it a chemical reaction or a physical reaction? I couldn't figure it out, but what I do know is I had to try it for myself. So
you need to think, do you think this is a chemical reaction or a physical reaction? Think about it. Is it chemical or is it physical?
With the help of a high-speed camera, we should be able to tell exactly what's going on. So I'm going to be using this Morgan kosher salt, but I'm pretty sure that any table salt will work. And yes, you actually can melt table salt. It has a melting point of 1,474 degrees Fahrenheit or 801 degrees Celsius. When it's molten, it's very water-like and fluid, but it quickly hardens into a massive crystal and makes a cool noise when it cools down. This is a small stainless steel shot glass crucible I found at the thrift store, and it holds about 50 grams. Okay, exactly 50 grams of sodium chloride. Next, I put it into my furnace, turn on the propane, and just blast it until it melts. This takes about 10 minutes, and you can tell when it's melted because the bright yellow sodium flames coming out the top. Well, let's put it into my high-tech pouring device and see what happens. That wasn't too bad. We survived. Well, I was expecting an explosion, and that hardly splattered at all. I'll try this again. 2, 1. Alright, now I'm getting pretty disappointed. I thought this would explode, so I heated it up really hot, and I said I'm going to pour it in as fast as I can. And 3, 2, 1. Oh my god! No way! This explosion was totally awesome and a total surprise. I was expecting a little bit of splattering, but what I got was like a full-on, powerful explosion. Look at the cavitation bubbles on the glass, and it just shattered it and blew that fish tank glass across my...
So what's causing that explosion? Chat with your neighbor. What's happening? What's causing that explosion? Pardon me? No. There's a reason that we watch these videos.
my yard.
Okay, we're going to see if he explains it. If not, we'll talk about it.
Try again. Plus, an experiment has to be repeatable to be valid.
Oh, look, we're going to try and repeat it.
That last shot was awesome, but I think it was a little bit overexposed, so I put a zoom lens on it and I cranked down the exposure so it'll be darker and maybe we can see better what's going on. 3, 2, 1. Oh, I'm so scared. Yep, that was an explosion. Even at 7,000 frames per second, the explosion is nearly instantaneous. You can see just a small amount of sodium chloride salt will create this huge gas bubble. And just when I think it's over, there's more little explosions happening on the inside surface of this gas bubble. And just
So what is that gas? What are the two things that are in that container? We have water and salt. So unless there's a chemical reaction, chances are that that gas is either water or salt. Which one do you think is more likely? Water. So that hot salt is going into the water. What happens to water when you heat it? It boils. So essentially what you're getting is you're getting a very, very fast, very explosive boiling. Okay, so this is actually a physical change, not a chemical change. It's nothing to do with the salt, it's just the fact that it is so hot. At least that's what I believe. Let's see if he has anything else to say about it. But that would be my best guess.
just when I think it's done, boom. You know, that actually looks pretty peaceful. I mean, pretty peaceful for a cloud filled with molten salt expanding at several thousand feet per second that's trying to kill you. Still looks pretty nice. A close-up view is really interesting. Now I wanted to see what a wide-angle shot would look like. 2, 1. Cool. It's really interesting to see the force of this explosion. The glass on the fish tank flexes back and forth, and the whole thing jumps up and into the air. Probably displaced about 2 gallons of water in the fish tank. This did end up breaking my fish tank, but not really. It just separated the glass from each other without breaking it. Now we're bumping it up to 21,000 frames per second. A little bit smaller resolution, but we gotta try. Alright, so we got a new fish tank and we're ready to try some other salts. The first one we're going to try is Borax. It's like a laundry detergent booster.
Okay. Okay, so do we have the difference in our head now between molten versus aqueous? Okay, very, very different. Next page. All of our changes of state. I'm leaving things everywhere, as usual. All changes of state are physical changes. There's no new substance produced. You are responsible for knowing what they are called, okay? So hopefully, some of these are really easy. Melting is when you go from a solid to a liquid. What do you call it when you go from a liquid to a solid? Freezing. Oh yeah. Liquid to a solid is freezing. So, at what temperature does salt freeze? 801 degrees Celsius. Because the melting temperature and the freezing temperature are the same. Water freezes at 0 and it also melts at 0. So iron melts at, or not iron, sodium chloride, salt, melts at 801 degrees and freezes at 301 degrees. Yes? It's actually going back and forth between the two states when it's at exactly 0 degrees. That's why sometimes you'll end up with like sleet, you know, coming down. It's not really solid, it's not really liquid, it's sort of in between, right? You've got a mixture of the both. Yes. Probably a mixture of both. With some of the molecules turning into solid and some of the molecules turning into liquid and going back and forth between those two states. Yeah? Okay, what is it called when you go from a liquid to a gas? Vaporization, or what else? Evaporation. Okay, so vaporization or evaporation. When it goes from a gas to a liquid, that is called condensation. Hopefully those ones are familiar to you, but you might find that the next two are a little bit strange. If you go directly from a solid all the way over to a gas, can you think of a substance that does that? Dry ice goes straight from a solid to a gas. That is called sublimation. How many people have heard the word sublimation before? Maybe you heard it in grade 8. Okay, so yeah, it's a familiar term. Going backwards, basically what's happening is the gas deposits as a solid. So we call it deposition because the solid deposits. So gas to solid. Okay, that's called deposition. Sublimation is solid to gas. Okay. What is the melting point of water? 0 degrees Celsius. Would you like to see some water melt? Okay, let's watch some water melt. Ice. Solid water melts. And there's not actually any speaking with this, so it's just to watch. So this is solid water. Can you see the little Mickey Mouses? They're like little hydrogens on sticks sticking off the red oxygen. That is our solid water. You notice how there's big holes in the structure? Do you know how ice floats on water, like on liquid water? It's because in solid form, the water molecules arrange themselves with these big gaps in between. And those big gaps make ice less dense than liquid water. Because liquid water, the molecules don't have those big gaps in between them. They just pack as closely as possible. Yes? Yeah, it would suck, wouldn't it? Yeah, it would just be wrong. Wrong. Okay, so here's a bigger piece of ice. You can see it in 3 dimensions, sort of like a slice of ice. And now it's going to start to melt, I believe. We're zooming out. Oh, now we're not melting yet. We've made a bigger crystal. We've made an ice cube. Okay. Oh, and now we're starting to melt. So do you remember when we were talking about that water at 0 degrees Celsius? Do you see how some of the water molecules are coming off and then they're going back on? That's like the melting and refreezing that would be happening at 0 degrees. Yeah. Or even if you've got ice water, right? And you've stirred it really, really well and you've got enough ice in it that it's all a uniform temperature, it will be doing this. What's happening to the structure at the edges? It's melting. That structure we now have, yes, we have the ice with a small layer of liquid water on the edges. So yes, the ice is wet. It's a simulation, yes. We can't actually look at molecules in this detail. Anyway, that was ice melting. Whoops. We're going to skip the connection to last year with density. You can read it if you want to. And now we are going to look at a simulation of freezing. What is the freezing point of water? 0. What is true of both the melting and the freezing point of water? They are both 0 degrees Celsius. They are the same. Yeah, yeah. I know, these double blocks do me in. All right, let's take a look at this one here. Make it bigger. Bigger. There we go. You could, the only reason I like this one is because the molecules are a little bit bigger and easier to see. And it's got the nice sound effect with it. Freezing. Should we watch it again? Oh, what am I doing? Ah, there we go. Anyway, there we go. So that was freezing. Whoops. Okay, back we go. Now, boiling and evaporation and vaporization. Boiling takes place at the boiling point. So for water, what is the boiling point? Yeah. Does evaporation, do you have to have 100 degrees Celsius for evaporation to happen? No, if you have a puddle of water on the desk and you leave it there over the weekend, it's going to evaporate. Exactly. So evaporation can take place at any temperature. And it does take place because, do you remember when you saw like those little water molecules coming off the ice? The same thing happens with evaporation, is that some of the water molecules will turn into a gas, but once they've turned into a gas, they can just float off into space. Yeah, so if they just happen to break off, they'll just float off into space, and now they're a gas, and that's at any temperature. But they're both liquid going to gas. Evaporation is liquid going to gas. Boiling is liquid going to gas. Are you guys familiar with the term molecule? Do you know what a molecule is? It's a molecule. It's a little bit of matter. What it is it's a little bit of matter that is made of two or more atoms. Okay, so a molecule is made of two or more atoms. So when we look at water, we don't say a water atom, because that would mean just one little ball, right? What's water made of? How many atoms is water made of? 3. There's 3 atoms in water. Three atoms make one water molecule. And these are our little molecules of steam here. These are our molecules of liquid water. And we're going to let Tyler talk to us, my friend Tyler, talk to us about evaporation or boiling. I know, it would be nice, wouldn't it?
Here's one of the biggest things.
Okay, make that big. Okay.
Here's one of the biggest things that people don't understand in chemistry. Keep this in mind. When a liquid boils or evaporates to become a gas, the molecules don't come apart. So let's talk a little bit about liquids, evaporation, boiling, and molecules. So here is a very tiny glass of water. Well, it's a tiny glass of water that we've zoomed in zillions and zillions of times so we can see what makes it up. And what we see is that this glass of water is made of all of these water molecules. One oxygen atom connected to 2 hydrogen atoms. That's why we call it H2O. So our glass here contains lots of molecules of liquid water. Let's now make some steam, some gas water. What we're going to do is we're going to heat up this liquid water. And as we heat it up, the molecules in it are going to start moving faster and faster and faster until some of them are moving so fast that zoom, they can jump, shoom, right out of the liquid water, enter the air above that liquid, and start flying around. Now, these guys up here are molecules of steam, also known as gas water. So here's the main point. When they're liquid water, the molecules H2O are packed really close together. When they're gas water, or steam, they're still molecules of water, 1 oxygen and 2 hydrogens. It's just that now they're not as densely packed and they're flying around in the air above the liquid. Here is the mistake that so many people make and that I don't want you to make. This, as we said, is the way that water does evaporate. Here's the mistake that people make. Here is another glass of water. So many people think that when water molecules become gas, that they have to break apart, that the atoms that make up those molecules split apart from each other. And that's the only way that the liquid water can become gas or steam. So we have these molecules here, and they have to rip apart, rip these atoms apart. And so that if we were to zoom in and look at steam, we wouldn't see water molecules, but we'd see all of these pieces of the molecules, all these atoms ripped apart.
Which of those is correct? The one on the left, okay? This one is correct. This one is often what people think happens, but it's not. Otherwise, how would you get water back again? You wouldn't, right? This is a physical change. You start with water molecules. What would this be? You start with water molecules and you end up with separated hydrogen and oxygen atoms. What kind of a change would that be? That would be a chemical change, but it doesn't happen that way. Yes, yes, yes. So when they become like H2O, they become a liquid. It has to, can I answer that question for you later? Because it's got a bigger explanation than we maybe have time for right now. Yes?
This is wrong. Here's the big red X. I don't want you to make that mistake. On the other hand, here is the right way that boiling or evaporation happens.
The molecules look just the same in gas as they do in liquid. They do not, big red X, they do not split apart into the atoms that make them up. Same in liquid, same in gas. Okay, now this isn't just true for water. This is true for anything, for any liquid that can evaporate or boil to become a gas. So here I have a tiny amount of gasoline. The molecules look like this. 8 carbon atoms surrounded by 18 hydrogens, and then here I have some alcohol, a carbon with a bunch of hydrogens, and then an oxygen. Now, alcohol and gasoline can both evaporate. If you're like me, oh, you love the smell of gasoline, which is like those vapors you get when you're filling up your car. Oh, I love it. So you know firsthand that gasoline can evaporate, become a gas. Here's the point, though. Here's the wrong way to think about evaporation. If a gasoline molecule looks like this, the wrong way to think about it is that these molecules would come apart into the pieces and into the individual atoms. And the same thing here with the alcohol. This is wrong. These molecules here have split apart into atoms and pieces of molecules. On the other hand, the right way to think about this is that both the alcohol and the gasoline molecules just nicely lift out of the liquid when they turn from liquid to gas. This is what the liquid would like. Would look like. The molecules are all tightly packed together, and here's what the gas would look like. The same.
Yeah, do you remember back when we were talking about matter and non-matter, and we said that a smell was actually matter? So I'm not sure what Tyler was talking about with loving the smell of gasoline. That was a little strange. However, we all know that you can smell gasoline, right? We've all smelled it. And that's because these little molecules will go up into your nose. You'll breathe them in along with your air, and they'll attach to receptors in your nose. And that's what lets you smell them. And it becomes pretty obvious when you look at them this big, this blown up, that's matter. That's made of atoms. It's matter.
Molecules, they're just floating around in the air and they're further apart. So once again, don't make that mistake. Always remember that when a liquid boils or evaporates to become a gas, the molecules don't come apart.
Okay. Probably not as much as I do. Okay. Let's fill this in together. A molecule is a type of, hold on. A molecule is a type of particle. An atom is another type of particle. Which one is the bigger particle usually? The molecule. Now, if you had a little tiny molecule like say H2, because the atoms are so small, it might actually be smaller than a really big atom like a uranium atom. But in general, the molecule is bigger. How many atoms is a water molecule made of? 3. Molecules are always made of 2 or more atoms. What type of elements, this is going back to our periodic table stuff, what types of elements are hydrogen and oxygen? And usually if we are asked about the type of elements, we are looking for the categories either metal or non-metal. So what are hydrogen and oxygen? They are non-metals. And it's interesting because molecules are always made of non-metal atoms. No metals allowed. If you mix metals, you end up with an alloy. So what'll happen is you would have to melt one metal and melt the other metal. and then you can pour them together and mix them around. And that's different than, say in water, you always have to have 2 hydrogens for every 1 oxygen, right? Always H2O, never H3O or anything like that. But if you mix 2 metals, you could have, let's say you mix silver and gold, you could have 75% silver, 25% gold, you could have 50-50, you could have 80-20. So alloys are different in that there's no specific ratio between the atoms like there is in molecules. Yeah. All right, and we can just see these pictures that Tyler provided us with. The atoms in a molecule are stuck together with very strong bonds. Very strong bonds. So if I was to look at this water and I said, oh, it's attached to that, the hydrogen is attached to an oxygen and the oxygen is attached to a hydrogen. If I were to draw that over here, that attachment between them is a very, very strong bond. Okay, that's a really strong bond. And we're getting a little tiny preview here of our next unit. You don't need this for this unit, but in our next unit, you're going to learn that those very strong bonds between nonmetals are called covalent bonds. So these covalent bonds, covalent, are very strong. And they occur between non-metal atoms. So covalent bonds is just non-metal to non-metal. When a metal gets together with a metal, there's a different kind of bond, and that one's really easy to remember because it's called a metallic bond. Okay, so when a metal is with a metal, that's called a metallic bond. But when a non-metal is with a non-metal, what do we call it? Covalent. A covalent bond. You can, and there's a third type of bond that happens between a metal and a non-metal, and that's called an ionic bond. You know how you have sodium and chloride? That's our metal. And we have our chloride. That's a non-metal. And that's an ion, and that's an ion. And guess what the bond between them is called? It's called an ionic bond, okay? Pardon me? That's not a molecule. What it actually ends up looking like is a 3-dimensional structure like this where you have alternating sodium, chloride, sodium, chloride, sodium, chloride, sodium, chloride. And this is your salt crystal, okay? So rather than forming like little tiny molecules, they form larger 3-dimensional crystals, okay? And then metals, metalloids tend to react, they form covalent bonds like nonmetals. So they will react with nonmetals, and metalloids and nonmetals form covalent bonds. All of this bonding stuff, though, is just a preview for your next unit, so you've heard the words before. Yes? Okay, that's not going to be on this test. So a covalent bond is a nonmetal and a non-metal. I think I want to kind of skip over this bit for now. Yep. We'll skip that bit for now. We'll come back to it later. Yes, of course. Shall we watch some gas to liquid? Okay, so this is distillation. Have you guys heard of distillation? Distillation. It can be a way of separating either two liquids with different boiling points or a liquid from a solid. It could be a way of separating the water from salt water. Let's make it bigger. Okay. So here we have a flask. There's a glass tube. We have another glass tube. And in fact, this is a double tube. There's water on the outside that cools it down. And then on the inside, whatever gas comes up gets cooled by the water and it condenses. Okay, so it gets, the liquid gets heated, it rises, and then as it goes into this tube, the cold water running around the outside causes it to condense. So it's going from liquid to gas and then gas to liquid. So let's watch what happens here.
When performing a distillation, first the condenser is filled with cold running water. Next, heat is applied to the mixture which is to be distilled. The mixture is heated until it boils, and the hot vapors will travel up the distillation head. Measuring the temperature of the vapors helps us to identify the liquid being distilled and will help to confirm its purity. If the vapors are pure, they will have a constant temperature equal to the boiling point of the liquid being distilled. As the vapors travel into the condenser, they will be cooled and will liquefy. The liquid droplets, called the distillate, run down the condenser and are collected in a receiving flask. A liquid can be easily separated from non-volatile contaminants by using a simple distillation apparatus such as this one. Since the non-volatile components in the distillation flask will not evaporate, the vapors and the resulting condensate will be pure.
Okie dokie. Now, when is lunch? Lunch is at 11:45. Okay, so we have 10 minutes left. I will see if we have the components of it, okay? I'm going to get you for the last 10 minutes to go to somewhere near page 43. Let me see. Have you done page 46? Yes. No. Okay, so I'm going to get you to take a look at page 45 and then do page 46. Okay? So take a look at page 45, and actually we have 2 days, so do page 46 and 47, okay? So pages 45 to 47. Yeah, go, yeah. So that would be pages 45 to 47. If you found the quiz today difficult, what should you do? A, study, but also B, come see me during flex time. If you cannot make it to flex time, you can also probably drop by after school today because I'm staying for a while. Okay, so if the quiz was difficult, come to flex or after school today. I would like to help you with this before your test on Monday. Okay? That's next Monday, yes. Well, it's hard to do this Monday because we got trouble back in time. That would be nice. Trouble back in time. Well, they always get trouble back in time. Oh, so it's stuck back there. Oh, I'd probably just go back to like, okay, so that would be another like critical practice again, because I feel like. Oh, wait, no, I just forget. Yeah, oh, like I went, like I've already been back to the 70s. No, I've lived through the 70s. Oh, no, and then the reason I would probably go back then is I think like a lot of the medical skills and all of those things were at least developed enough that modern medicine, antibiotics, control pills, all of those things that make your life so you don't have to like, get sick, have babies you don't want, right? Like yeah. I feel like the 1970s. Yeah, we just got back in time. Yeah.
Because I like this.
The only reason I would go back to the 70s is because like climate change right now disturbs me, and I would like to not live over it. Yes. Oh my gosh, yes. I was rich.
Wait, let's say I'm going to invest $1 million. Wouldn't that change what the house is?
Hi.
How much of this is on the bus?
Well, you need to know the names of the changes of state. You need to know how to represent solid, liquid, gas. You should be able to recognize from a picture which state you have. And you should know that in a physical change, you have no new substance. Mostly this was just kind of like, let's see some pictures of things, like, and so we can actually visualize what's happening, because that'll become important in our next unit. Yeah. Yeah, but it'll also have like things about the periodic table, so alkali metals, alkaline earth, all those things. There will be some stuff like that. There will be things about properties, chemical and physical changes. I have review material, and if it turns out we're not ready by Monday, then we'll put it on Tuesday. You know what I mean, right? Like I set Monday as a goal, but we might, because of these long blocks, it's not like we, I don't think quite the same. I only see you twice this week. So I'll put it on until next week. Yeah. Yeah. Thank you. How you doing? Good. I'm good.
Oh my God.
Would Mr. Ryan please call the office? Mr. Ryan, please call the office.
Oh my God.